that you have in mind. For example, there are some consistency conditions that you have in mind. For example, you want them to be anomaly free. And as long as they're anomaly free, as long as they, they're consistent by QFD standards, they're good QFDs for you. But the idea of Swampland Program is that when you add gravity to the mix, then suddenly things can change. And the EFTs that can arise as the low energy effective field theory of quantum gravity can be are much more special, are much more restricted. And this is a nice schematic to just demonstrate the idea that, for example, if this is the space of all anomaly-free QFDs, the ones that we know they arise from something like string theory, from some UV complete theory of quantum gravity, are is like almost a measure zero subset. Now, when that's the case, when you have such a small set, and you want to study that set, then you have to have kind of infinite precision to exactly find those. So instead of exactly finding them, a better approach might be to converging to them by ruling out a continuous region. For example, by coming up with some criteria that could tell us what's not in the landscape. And by landscape, I mean the theory is consistent with quantum gravity. What's not in the landscape of quantum gravity, and rather than what exactly is. And these criteria that tell us what QFDs possibly do not have a quantum gravity UV completion, these are called Swampland Conjectures or Swampland criteria. And the Swampland program, so Swampland are bad EFTs and landscape are good EFTs in the sense that whether they're compatible with quantum gravity. And the idea of Swampland program is to figure out these criteria, figure out what really quantum gravity implies about your effective field theory. Okay, so let me talk about two conjectures more specifically because I'm going to focus in on them. The first one is the distance conjecture. Now, the distance conjecture, the formulation of it is quite simple. It tells you that whenever you have a moduli field, which means that it's a massless scalar field that you can set its value at infinite at infinity of space-time, it's your boundary condition to anything you want. Okay, so the distance conjecture, it says that if you take the VEV of any scalar field to infinity, then a few specific things need to happen. The first thing is that there's always a tower of not just light particles, but like weakly coupled particles. Okay. Yeah. And more specifically, so as I take phi to infinity, the masses of this tower of particles go to zero, but in a very specific way, exponentially in my scalar field. Now, you might be asking me, well, I can just reparameterize my scalar field to be a different scalar field. And if it's exponential in the first one, for example, I can engineer my reparameterization to not be exponential in the second one, which is really important that the phi that we're taking here is the canonically normalized scalar field, meaning that the kinetic term of the scalar field is that like canonical kinetic term 1/2 d phi squared. And then lastly, not only there's always this tower with exponentially decaying masses, but there's also a universal minimum for C, meaning that you cannot take this C to be arbitrarily small. You cannot take this tower to be arbitrarily, its mass to be arbitrarily close to constant. There's a minimum universal minimum decay rate. Okay, now I sold you Swampland conjectures as something that is specific to quantum gravity. Let's see where quantum gravity comes into play for distance conjecture. So as far as field theory is concerned, it's perfectly fine to have a field theory without a tower of states. It's perfectly fine to not have, a tower of states with masses that go to zero in every direction. And it's actually quite eye-opening to see how string theory, for example, saturates, how it satisfies this conjecture in some cases. Yeah, so I'll give you an example in a moment, but before that, I just want to point out like the deep intuition behind the distance conjecture. So distance conjecture at its core, it's a quantitative version of the statement of duality. So in string theory, whenever we go towards infinite distance in every element of the moduli space, there's always some description that becomes valid for the light weakly coupled particles in that corner of the moduli space. And the simple statement of distance conjecture is that, at every infinite distance limit, you have different light weakly coupled states, and there's a different weakly coupled description that describes those states. And the fact that any two limits that you get, there are two descriptions, means that those two descriptions are dual to each other. After all, duality just means that you have two weakly coupled descriptions that share the same moduli space. So in other words, distance conjecture is saying that dualities in string theory are not, just a random occurrence. There's something deeply quantum gravitational about it. Now, let me give one, I think, illuminating example. So let's say you take a field theory, you compactify your field theory in a circle. And then I take the limit where, so when I compactify my theory in a circle, the radius of the compact dimension becomes a field in my lower dimensional theory. Now I can change the value of that radius in the lower dimensional theory, and I can ask, where is my tower of states? Am I getting a tower of state with masses that go to zero? So if I take R to infinity, it's very easy to see where that tower of states comes from. So the tower of states are simply the KK tower of the light particles of your higher dimensional theory. Because when you compactify a theory, every particle comes with a tower. And this tower corresponds to momentum along the compact dimension. So these are called the KK tower. And their masses go like 1 over R. So when R goes to infinity, 1 over R goes to 0. Moreover, when you do the math carefully, when you find the scalar field that's canonically normalized, you'll see that R is not canonically normalized, but log R times some constant is. Therefore, 1 over R is indeed exponential in the canonically normalized field, which is log R. Okay, so in the direction of R goes to infinity, everything checks out. We get a tower of states with exponentially decaying masses. What about the other direction, when we take R to 0? The KK states their masses go to infinity when you take radius to 0. Where are the states that their masses go to 0? So string theory solves this for us by inclusion of strings, because in string theory, you also have these weakly coupled strings that can wrap around this compact dimension. And when you take your radius to 0, now the masses of these stuff goes to 0. So, and these are things that are not there in your effective field theory. So when you include strings, and only when you include strings, it's really clear to see that why and how this happens. And I mean, it could be like other objects in your theory, but with the addition of strings, it's like really clear that that these winding states, their masses goes to 0 when you take R to 0. So as you can see, it's non-trivial way that the theory can satisfy this. And interestingly enough, we see that in all the many constructions that we have in string theory, this is always satisfied. So this is the distance conjecture. Now, let me also talk about one other conjecture in a little more detail compared to the other conjectures that we're talking about. And these two are the ones that we'll particularly focus on. So this one is the Trans-Planckian censorship conjecture. Now, in cosmology, when we have an expansionary solution, you start with some modes with some physical wavelengths, and the expansion of the universe stretches out these physical wavelengths for you. And if you put any cutoff for your theory, there's always modes that have wavelengths below that, meaning that they're UV. And then because of the stretching of the universe, they become IR, they go to the other side. And this really is telling you that you cannot put any cutoff of the theory and say that, these modes just don't talk to these modes. And this, I think, is the easiest way of seeing why gravity is not renormalizable. Because as opposed to the other fields where you can, put this cutoff and the UV modes do not affect the IR modes, in gravity, whatever you do, the simple fact that you have expansionary solution prevents you from doing that. So then the question becomes, okay, is there an analog of renormalizability? Can I impose something similar to that? And one thing that you can put is that, okay, maybe I don't have like a clean cutoff, but maybe my UV cutoff or IR cutoff are at least interconnected. There's some UV IR connection in that sense, when I'm doing physics. And a natural UV cutoff that you put in quantum gravity would be the Planck scale, and a natural IR cutoff that you put in expansionary solutions is the Hubble scale, because everything that extends beyond the Hubble scale, it classicalizes and freezes out, meaning that the expansion of the universe is so fast that the mode cannot react to it. Therefore, the peaks of the modes do not talk to each other anymore, and they just freeze out. So it just stretches out. So the Trans-Planckian censorship conjecture, the statement of the conjecture is very simple, that in any theory of quantum gravity, if you start with Planckian modes, and if you go through some period of expansion, and then these modes expand, they can never expand so far that they exit the Hubble horizon and become classical and freeze out. So if I want to put some math to what I just said, it would be that if I start with this initial wavelength L Planck, and if I multiply this by the amount that it's going to stretch out, which is the ratio of the scale factor at final time divided by the ratio of the scale factor at initial time, then my new wavelength should be smaller than my Hubble horizon at my final time. So this is the statement of Trans-Planckian censorship conjecture. And one of the nice things that it does is that it puts a very universal observation in string theory in cosmological terms. And I will come back to that observation because it's quite important for us, and probably a slide or two. But are there any questions about the statement of these two conjectures so far? The distance conjecture and Trans-Planckian censorship. And if I went too fast, please let me know. It's okay. I can just say that we're. All right. Okay, so now let's see what does TCC, and from now on, I'll refer to Trans-Planckian censorship conjecture. Let me refer to this TCC. It's much shorter. So let's see what TCC tells us. So TCC is telling us that if you have this accelerated expansion, it cannot last like that fast forever. It must have an endpoint, or at least it must slow down. So that's technically what it tells you. Now let's see what it tells you in specific setups. So for example, if you have a potential like this, and you have your universe can be stuck in a metastable de Sitter space, because when you're in the minimum of this potential, the value of the potential would be your cosmological constant, and it is metastable because you can tunnel out of it, and the process to tunnel out of that is through like Coleman-DeLucia instantons or Hawking-Moss instantons. Now, in either case, there's some finite lifetime associated to that metastable de Sitter. So TCC is telling you that either through those processes or through some other processes, you need to tunnel out before you violate TCC. And the time scale to violate TCC, the time scale for Planckian fluctuations to exit Hubble horizon, is 1/h log m Planck over h, or 1/h log 1/h in the units of m Planck. So this is what it tells us for metastable de Sitters. Now for unstable de Sitters, it's a little more complicated, but essentially the physics of it is that it's telling you that even if you're here, it cannot be too flat, the potential. I mean, the first derivative is 0, obviously, but the second derivative cannot be too small, because it's telling you that you should have enough slope nearby this point to make sure that the quantum fluctuations will drive you away from that fast enough so that the de Sitter state here is not stable enough to violate TCC. So that's what this condition is telling you. And these A and B are some dimension-dependent constants that you can see in the original paper. And finally, the more interesting case for us, at least in this talk, is this case that tells you that if you have this runaway potential, and if you want to make sure that runaway potential satisfies TCC, it's telling you that it must exponentially decay. And moreover, this coefficient in the exponent should be greater than some constant. And this is the universal observation in string theory that I was talking about, that in string theory, all like in many examples that we have, people disagree all the time over, what happens here inside the moduli space. But usually when you take phi to infinity, as I explained earlier, there is a weakly coupled description, and that's where we can do our calculation the best. And in all of those examples, if v is not zero, it's always exponential. And there's always a lower bound for that exponential for how quickly it goes to zero, for the coefficient of the exponential. So and TCC puts that in a very cosmological, in terms of a physical process, which is nice. But I mean, nice doesn't cut it. The question is it true? And we'll come back to that. Okay, so let me talk more about this lambda and the phi. So let's say you have an exponential potential, as is universal in string theory. Now, what does TCC tell you about this lambda here? Now, if you just focus on the potential, if you say that my potential is the only thing that drives my cosmology, then you find this bound. The lambda is bigger than 2 over square root of t minus 2. However, for example, there could be a situation where I mentioned that there's a tower of light particles. Maybe they become light enough to mess up the cosmological evolution. Maybe they become light enough to be excited and contribute to the cosmological evolution. And in that case, you cannot have the strong bound, but you have a weaker bound. However, there's reason to believe that the second case will never happen. I won't go into it in detail, but it's very reasonable to say that's probably always the first case. So as you can see, TCC gives you a very specific number for this lambda and the exponential. And before going forward, so there's a specific number for the lambda and the exponential that you can check in many different string theories, and all of them seem to satisfy so far. Okay, now so far I talked about why it's compatible with string theory, what is it, what it means, but why are these stuff interesting phenomenologically? I mean, we're talking about quantum gravity. So, I mean, if we can't see anything about it, who cares? So and what I want to mention here is that these things might be more relevant to phenomenology than you might think. So for example, the two conjectures that I mentioned are directly connected to early universe cosmology, in particular inflation. So first of all, both of them are in tension with inflation. Now, the reason is the following. Let's first focus on distance conjecture. So distance conjecture is telling you that if you take the VEV of your phi and vary it too much, then you get this tower of light states. Now, if you put a cutoff and these states become lighter than the cutoff, then you have to integrate them back in. So the EFT that you would use otherwise breaks down. So distance conjecture is really telling you that field theory with a fixed cutoff has a limitation. And that limitation is a field range of the order of Planck scale. And if you go beyond that, there are these states that become lighter than your cutoff, and your effective field theory breaks down. Right? Before that. So, but you see, this is just on the nose in tension with a lot of inflationary models, because in conventional inflation you have these very long Planckian field ranges. So it's not in contradiction, because I mean that's 60 M Planck. You can say that here it's like O of 1 M Planck, but it's in tension nonetheless. Now, TCC is probably even worse, because so TCC tells you that, I mean, you can kind of immediately see why it doesn't like inflation, because in inflation, kind of the whole point is to make sure that these quantum fluctuations exit the Hubble horizon and come back, and they're the CMB modes that we see. And if you don't start with Planckian fluctuations, and if your sub-Hubble fluctuations exit the Hubble horizon and they're your CMB modes, then you have an initial condition problem. That why we're there in the vacuum scale invariant state that we see today? Because the solution of inflation usually for this is that even if they weren't in the beginning, they would become the scale invariant vacuum fluctuations, because eventually the Planckian modes will take over. So because of that, you can immediately see why it should have some tension with inflation. But when you put numbers to it, you see that in the conventional cold inflation single field models, the simplest ones, it first of all puts a strong upper bound on the energy scale of inflation. But more importantly, it puts a very severe bound on the field range of the inflation. It tells you that it must be smaller than 10 to the negative 31 in Planck. When you impose TCC, but also demand consistency with observational data. So this is something that we did in this work. And we also showed that when you put a field range so small like that, you immediately run into initial condition problems because, for example, you cannot have slow roll trajectories anymore. The idea of slow roll is that even if you don't start with slow roll, you will converge to slow roll. But if your field range is so small, you do not have the time to converge to slow roll. So you run into inflation due to initial condition problems. Yeah, so they're either, the models are either usually inconsistent with TCC, or if they are consistent, they usually have some sort of initial condition problems. Now, I must say that there are some like more exotic models, for example, like having, instead of one inflationary era, having multiple inflationary eras, or there are like other solutions that are not inflationary that are like consistent or in less tension with TCC. But here I focus on the like conventional inflation. Okay, so the first part was about distance conjecture and TCC. So hopefully I disambiguated the like half of the title. Are there any questions about that?
Hello, Alek. I would like to ask
Yes.
a question about the tension. What do you think about the eternal inflation? Do you think does it predict a condition for inflation?
That's a great question. So and I'll actually touch on that like very soon. So in one setup, we saw that in a setup where you have a potential that has kind of a lot of metastable minima, and you can tunnel from one to the other one. Interestingly, we saw that if you apply TCC to each one of those metastable minima, the condition that you get is like it derives the no eternal inflation condition for the effective evolution in general. But I can't say that it always gives you the eternal inflation. So I'm not sure. So in some sense, they're different because for a generic potential, one of them, the condition is it compares v prime to v, the other one compares v prime to v to the 3/2, if I'm not mistaken. So in general, in the inside of the moduli space, they're different. So you can say, like one could be correct or the other one. But it seems that at least there's some connection based on that setup. Yeah.
Thank you.
Yeah, no problem. Thank you for the question. Any other questions? Okay, so I told you about these two Swampland conjectures, and now let me tell you how do we get these. I mean, I told you about their consistency with string theory, but is that really the only way that we motivate Swampland conjectures? Is this like some glorified, string theory that I'm just doing in terms of effective field theory? And spoiler alert, no. So so there are really three ways that people motivate Swampland conjectures. The first one is if you can find some connection between the conjecture or the condition or whatever you want to call it with some more fundamental principle. This could be unitarity, causality, black hole physics, like Hawking radiation, could be ADS-CFT, something like that. Now, the second one is, maybe I can skip I can go back to these in the Q&A if you want to give you an example of how, for example, this works for some of the Swampland conjectures. Now, the second one is if you have evidence from string theory, and this is what I told you, for example, about TCC. People have tested it in many different string theory setups, and they've seen that it works. And the third one is if you have, so this like a web of Swampland conditions, some of them are more connected to fundamental principles, so much so that at this point we like believe in them. TCC doesn't have that level of support, but for example, something like no global symmetry conjecture, it essentially says that every symmetry, if it's exact, is not a gauge symmetry. Sorry, it's not a global symmetry, it's a gauge symmetry. That's the statement of no global symmetry conjecture. And you can make argument for it based on black hole physics, based on holography. You see like a remarkable consistency for various generalizations of it in string theory, and it has a lot of support. So you have this web of conditions that some of which are very like they have a firm foundation, and then you can ask how consistent and compatible these different conjectures are within themselves. And usually there are connections that you wouldn't expect them to be there, but you suddenly run into them. And I mean, this one isn't kind of an expected one. So for example, people have shown that a generalization of the no global symmetry conjecture implies a different Swampland conjecture, which tells you that whenever you have a gauge symmetry, you must have all charges, all representations of the gauge symmetry. We can show that this follows from a version of the no global symmetry conjecture. But particularly, for example, just to give you an example, I mean, there are many examples like this, but just to give you a taste of what I was talking about these like unexpected connections. This is the same setup that I was explaining to Omar a minute ago, that, for example, if you take this top form of the theory, let's say you have a four-dimensional spacetime and you have this top form, and the things that are charged under this, they're domain walls, and on each side of the domain wall, the energy jumps. And the potential that's generated by this, let's say, is something like this, where the domain wall transitions from one metastable to the next metastable for you. Now, as I said, for example, we showed that the condition for each metastable, the sitter here, to satisfy TCC, turns out to imply that you can never have eternal inflation, which is a different conjecture that someone else proposed in the context of Swampland. And even more surprisingly, the TCC for each one of these transitions also tells you something about the domain wall for this transition. And there's this other conjecture called weak gravity conjecture. It started about black holes, but then people generalize it to higher dimensional brains. And TCC implies that for these domain walls, which was very non-trivial. Now, maybe at this point, I don't want to go into, it's better if I don't go into like what weak gravity conjecture exactly is, but please ask me in the Q&A. I would love to, go into details of this or any other Swampland conjectures for you. Yeah. Okay, now let's go back to TCC and distance conjecture. So these are really interesting. They're phenomenologically relevant, both for particle physics and cosmology. How good do we know them? How good are our motivations for them? So we have a lot of evidence from string theory. We have connection, lots of connection to other Swampland conjectures, but can we connect them to fundamental principles? And this is the part that was lacking for at least TCC and to some extent distance conjecture. And today, I want to tell you that why you can kind of, they actually very nicely are connected to holography, to the most basic version of holography. And hopefully you'll believe in at least some part of these conjectures by the end of this talk. Okay, so let's start with holography and what I mean by holography in this talk. So the first thing that I want to mention about like holography and the unique features of quantum gravity that are informed by it is that we've learned that in quantum gravity there are no local observables, and there are 100 different arguments for it, maybe not hundreds, maybe 10 different arguments for it, but I think a very natural and intuitive one is the following, that in quantum field theory, you start with a space-time. You start with your manifold, then you define a physical observable at every point of that manifold. In quantum gravity, you don't have that sharp, nice manifold because you're supposed to sum over different manifolds. So if you have different manifolds with even different topologies, then you cannot take that and then define like local observables on it. So local observable is not the starting point of quantum gravity. It's an emergent approximation of quantum gravity. Now, yep. So then you can ask, so what is the what are the observables in quantum gravity? Now, the observables in quantum gravity are boundary observables. So we cannot fix stuff inside what happens in space-time, but we can fix stuff on the boundary of what happens in space-time. And then you sum over all the possibilities on the inside. This would be your path integral. And then one path suddenly, for example, is unshelled, one path is more dominant, and that would be your semi-classical approximation. But the fact that you can define the boundary still on the theory, the theory on the boundary is why in quantum gravity you always define your theory with boundary observables. And these are the stuff that we calculate in string theory always, because in string theory we calculate these worldsheet diagrams. And what's important about these worldsheet diagrams is that their legs are always taken to the infinity of spacetime, to the boundary of spacetime. So regardless of the shape of your spacetime, every time in string theory, when you calculate something, you're always calculating a boundary observable because these things are simply taken to infinity. And then the question is that what, I mean, of course I can write, I mean, I live in a world where the standard model is a quantum field theory. I write phi of x, I have electromagnetism. So when I say that there is an effective field theory, what do I mean by that? And that's a great question. And the answer to it is that in quantum gravity, what we mean by effective field theory is the effective field theory that best approximates these boundary observables that string theory gives you or quantum gravity gives you. So, for example, in the context of string theory, what this means is that in flat space, string theory produces S matrix for you, which again is a boundary observable. And then the correct EFD is the EFD that correctly reproduces those S matrix supplements for you. So that's really the essence of holography, that your theory should be defined based on boundary observables. Now you can ask, what are these boundary observables? So in flat space, this is S matrix, and presumably there's a lot of structure that quantum gravity would imply about S matrix that we still don't know all the structure for it. In ADS space, these are the boundary correlators in ADS CFD. For this one, we know much more about the structure the boundary correlators should satisfy. And for DS, so we don't know, we don't have a UV completion of this yet. But if an eternal de Sitter, for example, exists, there's actually a very similar procedure to ADS CFD that you can apply to DS. And it's known as DS CFD that again gives you these asymptotic boundary observables in de Sitter space. But you see, in ADS, you have this boundary in spatial infinity. In de Sitter, you don't have spatial infinity, but you have time-like boundary. So the time infinity, you have a boundary, which is when people define the boundary observables there. And I'll come back to that in a minute. Okay, now let me just, I just want to go over these three, and I want to tell you that why, like, holography really has one equation for these boundary observables. It's the same equation that applies to flat space, ADS, and DS. It's not like, these are not really that different in terms of the boundary observables. So let's start with a flat space case. So in flat space, you have LSC formula that gives you the S matrix, and I can rewrite the so first of all, if I here you can see that you have transform of your fields, so I just write phi in the momentum space instead. I move these propagators to the other side, so I get inverse propagators here. So my S matrix element, which here I've written it like this, is the limit of inverse propagator multiplied by some correlation function of my scalars in the momentum space. And here you should note that the p's on the left side are unshelled, so they're d-1 dimensional, but p's on the right side are off-shell, which means they're d-dimensional. And I should take these p's to go to these p's, I should take that limit. And the role of inverse propagator here is to make sure that the singularities of this expression are canceled so that I'm converging to something. So that's the role that it plays. Now, in ADS, very similar equation. The only difference is that instead of working in momentum space, we usually work in position space. So you take phi x1, phi x2, phi x3, phi x4, and this was supposed to be x4, and you take these to the boundaries of ADS, and you look at the correlation function. So I would love to say that if you just take the correlation function and you take these xi's to the boundary of space-time, it will converge to something. But unfortunately, it doesn't. However, I can I can factor out the trivial part, the trivial way that it changes using x, and then it will converge to something. And that's the propagator. So again, you multiply inverse propagator by your correlation function, you take the limit of it going to boundary, bam, that's your boundary correlation function. And the exact same formula applies to this zipper, that you these correlation functions, you take xi's to the boundary of space-time, and here it's the future infinity, and you take out like their trivial dependence by the inverse propagator, then it will converge to something. That would be your boundary observable.
Alek,
So
yeah. I'm sorry, I'm disturbing you. So we are officially, like we started 2 or 3 minutes late, so you're kind of officially at the end of your time. But you can use 5-6 minutes at the most. So I will not disturb you anymore, but I'm letting you know, all right?
Thank you. Yeah, I'll try to wrap up in 5 minutes.
Thank you.
Okay, so yeah, so as you can see, there's like parallel between the two equations. For the flat space, you have scattering amplitudes, and you work in momentum space. For ADS or DS, you have frozen correlators, which means that you work in position space. And the reason that we work with amputated diagrams is exactly because of these inverse propagators that we've multiplied here, that take out the loops and the propagators. Okay, now there are, I mean, this I've kind of explained. So yeah, this I've kind of explained. Okay, so so the question is, can we define these boundary observables in any effective field theory? And I want to show you that no, you cannot always define boundary observables in any effective field theory. In particular, when you have this V that goes to infinity and you have this quintessence-like models, if your expansion is too fast, you cannot define boundary observables in it. So let me, this is an argument for why you need, okay. So this is the part that's interesting to us. So if you take a metric for an expansionary universe like this, let's say you have a scale factor that depends on time. And the first question to ask is whether the boundary data that we define is scattering amplitude or frozen correlator. meaning that whether I should work with momentum space or I work with position space. Now, actually, I think that computation is here. So that depends on whether your particles can make it to the infinity or they cannot make it to the infinity. So for massive particles, you can calculate the distance that they travel. And if they don't make it to infinity, then you would expect Frozen correlation functions. But if they do make it to infinity, you expect scattering amplitudes. And you see that it gives you a condition like this. Like if you have a massive particle and ma squared remains bigger than t, then you expect to have Frozen correlator, otherwise scattering amplitude. And for massless particles, it kind of only depends on the scale factor. If the scale factor expands very sudden, then your photons freeze out. So you have to define Frozen correlators, but otherwise your photons do not freeze out. Okay. Now I want to look at the scale factors that depend very specifically on time, meaning that they depend polynomially on time. And the reason I'm focusing on this is because for potentials that are exponential in the scalar field, you get this kind of time dependence. And these are of huge interest to us. Okay, now let's do one page of calculation and I'll almost be over. So if you take a scalar field and you look at the equation of motion, it reads something like this. Now, if you do your normal mode expansion in a background with AFT that goes like t to the p, you get these quasi-stationary modes. And you can do mode expansion in terms of them. And you get these creation and annihilation operators. Then you impose the canonical commutation relations between phi and its conjugate momentum, which in effect will give you canonical commutation relations for creation and annihilation operator. And then you look at the vacuum of these and you calculate the 2-point function of phi. And then using the prescription that I previously told you, you look at the boundary correlation functions. And you see that it's trivial. It doesn't give you any non-trivial. In other words, when you take 2 points that they do not match, it's zero. The correlation function is always zero. So you don't have boundary observables in these cases. So the final lesson is that in these expansionary universes where you have a scale factor that goes like t to the p, whenever the correlation functions freeze, you never get boundary observables. So one consequence of that is that p is always bigger than 1, because when p is smaller than 1, everything freezes out. And I think, sorry, p is smaller than 1 because when p is bigger than 1, when the expansion is accelerated, everything freezes out. And when p is smaller than 1, then you find a bound on the mass. You find that the mass should decay fast enough. And so I'll just tell you that, maybe I won't go to the future slides. I'll just tell you that this p greater than 1, p smaller than 1 is exactly the prediction of TCC for these backgrounds. So this is proving you the TCC in the asymptotic region of the moduli space. In other words, this is giving you the bound on lambda that TCC gives you, this argument, this holographic argument. And for p smaller than 1, if you write this in terms of the scalar field that drives the cosmology, you will see that this gives you m smaller than e to the minus something times phi. So it gives you distance conjecture. So this is giving you a holographic argument for TCC and distance conjecture. I think I'll stop here. Thank you.
Thank you so much, Alek. I'm going to keep the recording going for the questionnaire as well. Are there anybody who wants to ask questions? If not, you will have to make do with one of my trivial questions, Alek.
Please, those are usually the best.
So I don't know this program very well. Apparently there are no questions as well, so I'll just ask. So when you told us about this no global symmetry conjecture, I genuinely do not know that, but it seems interesting. Why would anyone expect that to happen? Because like if you were to tell me like any symmetry will be, any exact symmetry will be local and you will be able to reach its full spectrum. somehow, I mean, like it will be there. Why would we expect the full spectrum to be there to begin with? I mean, from my knowledge of physics, I would not expect naively that to happen. And also, what does it mean for gravity? That claim, particularly for gravity. Can we? I mean, like, what does it imply? Is it in the lines of this? I forgot the Coleman-Mandula-like theorems, or I don't know. So I'm asking you a very general question about that particular thing you said.
No, those are great questions. So let me first talk about the argument for like a very hand wavy. I mean, there's a much more precise argument for it, but just to give you an intuition that where gravity comes into play for each one of these conjectures. So for no global symmetry. So something that's uniquely gravitational is black hole. And black hole is kind of culprit for both the no completeness of spectrum and the no global symmetry. For the no global symmetry, it's involved in the following way, that we know that if you throw a gauge charge inside the black hole, Hawking radiation will not violate it, because gauge charge is by definition the kind of charge that you can probe from infinite distance, right? So even if your black hole has a for example electric charge, that electric charge will be conserved throughout the Hawking radiation. But you see, if I throw a global charge inside the black hole, a kind of charge that I cannot measure from distance, I can only measure it when I'm exactly at that point. It's a local charge. Then it can be violated by Hawking radiation, because Hawking radiation doesn't care about what's inside the black hole. It cares about the horizon of the black hole. So if your charge doesn't leave any imprint on the horizon of the black hole, it gets violated. So that's the Hawking radiation of black hole violates the global symmetry, kind of.
Okay.
So that's one example. And then for the completeness of spectrum, just again, I mean, this argument doesn't tell you that why the full spectrum must be there, but just to give you an idea that why gravity likes to fill up the spectrum, again, black hole. So the black hole entropy law tells us that there's some number of microstates for black holes with a given charge and a given energy, and an energy and a charge window. And you can see that this is non-zero for all the charges, like even when you go up. So this tells you that, the black holes themselves can be the states that fill out the spectrum. However, it doesn't tell you about those low-lying states, and you can infer those from the no global symmetry conjecture.
Okay. Well, thank you. Any other questions?
Thank you for the question.
Yeah, of course. Thank you for the talk, by the way. It was quite nice.
Thank you.
All right, so we're a couple minutes behind our schedule. So if there are no other questions, I will just stop the recording.